So, with certain molecules, it seems like there are multiple Lewis structures that could be the right answer with the rules that we have. So, just the case with CO3 2 minus. So, let's see all the different ways we can draw it. CO, O, O, and then there's that 2 minus, which means there's 2 extra electrons here. It's 4 valence electrons, 6, 6, 6. In total, that makes 24. C is centered. Oxygen, oxygen, oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So all of our oxygens are filled, but we're missing 2 there. So we'll take these 2 and form that double bond. We need to signify that this is an ion, 2 minus. Now, since we have essentially identical bonds aside from that double bond, this double bond could go here or it could go there. And so we're going to show that with these resonance structures. So we'll draw another one, except this time we'll put the double bond here. And again, signifying that it's an ion. And then the third time, for that third and final bond, we'll put it on the right. Signifying it's an ion. And then that's our final way of drawing that because we've exhausted all 3 options for that double bond. Now we need to put these little arrows in, called resonance arrows, signify that in reality, all of the bond lengths are actually the same. There's not one that's shorter than the others and has that short double bond while the others have that long single bond. They are all somewhere in between, but we don't really have a good way of drawing that with our Lewis structures. And so this is the next best thing that we have. And so what these little arrows are showing is that it's actually somewhere in between all of that. But sometimes they're different and we're trying to figure out what's the best way, what's the truest way of showing it. So here we're going to figure out what the formal charge is. And the formula for formal charge is valence electrons minus non-bonding electrons, so lone pairs, and then the bonds to that central atom, or actually to the atom that you're addressing. And you have to find the formal charge of each element in that molecule. So let's start with the one on the left, formal charge of oxygen. Oxygen has 6 valence electrons. In this case, it has 1, 2, 3, 4 bonded to it. And then it has 2 bonds to it. I know sometimes we'll count a double bond as one item, but since there's 2 bonds in a double bond, it's counted as 2 when you're calculating formal charge. 6 minus 4 minus 2 equals 0. So the formal charge of this oxygen is 0. It's also the formal charge of the other oxygen because their bonding is identical if you look closely. Now let's find the formal charge of that carbon. Carbon has 4 valence electrons. It doesn't have any lone pairs right there, so there's no non-bonding electrons. It has 1, 2, 3, 4 bonds right there. 4 minus 4 is 0, and so the formal charge of that carbon is also 0. So that's looking pretty good. We got zeros across the board, but we still need to check the other molecules' formal charges. just in case. So the formal charge of this first oxygen, 6 valence electrons minus those 1, 2, 3, 4, 5, 6 non-bonding electrons minus 1 bond. 6 minus 6 equals 0, minus 1 equals negative 1. So that oxygen has a formal charge of negative 1. Formal charge of that carbon, we have 4 valence electrons minus 0 non-bonding electrons. 1, 2, 3, 4 bonds. Okay, the formal charge of carbon is going to be 0. And then let's check that right oxygen. Formal charge, 6 valence electrons minus 2 non-bonding electrons minus 1, 2, 3 bonds. 6 minus 2 minus 3 equals a positive 1, and so that oxygen has a formal charge of plus 1. And so the best resonance structure is going to be the one that minimizes formal charge. And since this one has that positive over there and it's negative over here, the one on the left is going to be better since it's zeros across the board. So this one has the best formal charge. It's the best structure.